Okay, this is Chapter 9, Section A, Modeling Our World. Basically, we're going to talk about how we use math to model different things that happen in our world that help us to make predictions. So we're going to learn to write and use linear functions, which describe straight line graphs. When we look at a scale model of an airplane. Well, a model is based on a relationship between quantities that can change, that represent something real, helping us to understand it. It represents something real and helps us to understand that thing. Based on relationship between quantities that change. So basically a mathematical model is something that we're going to use to represent something in real life. This thing can change based on the things that change around it. Functions. The building block of a mathematical model describes how a dependent variable changes with respect to one or more independent variables. Mathematical tools used to describe relationships between quantities, a single formula or graph. Not all relationships are functions, and for each independent variable in the domain, there corresponds exactly one value of the dependent variable. And we'll be talking about these two words a lot during this lesson. The dependent and independent variables. Variables are quantities related by a function. And this is the thing where in college algebra, we started talking about hold on one second. We started talking about variables is where we're starting to add letters into math. And that's when everybody's like, oh no, I don't like that. But we've got to be able to represent things that we're not able to represent in any other way. So that's what we use variables for. Now we've got basically two kinds of variables. It could be a dependent variable, and that's the variable whose value depends on that of the independent variable. So if we're doing something and we change the independent variable, what effect does it have on the dependent variable? Well, the dependent variable is going to change according to what the independent variable does, and we'll talk about that a lot more in these examples. But the independent variable is the variable whose value does not depend on the value of the other variable. So the independent variable can just exist by itself, and it's not going to depend on anything else. So we've got an example here, and it says temperature data for one day. And it says temperature depends on the time of day. Okay, so what do we know about this? Just by reading this statement, I know some things. Okay, one thing I know is it says the temperature depends. Well, right away, I know that the temperature is my dependent variable because the temperature depends on something. And in life, we know this. We know that it's usually cooler in the morning, and then it heats up as the day goes on, and as the sun goes down at night, it becomes cooler again. So the temperature is dependent on the time of day. Okay, so as the time changes, it affects the temperature. Temperature varies with respect to time. There is exactly one value of temperature for each time of day. So we're going to look at some examples of how to talk about variables here. And the first one says the total distance a car has traveled after various amounts of time during a road trip. Well, the total distance a car has traveled after various amounts of time during a road trip. The dependent variable is distance. Okay, so our dependent variable down here is the distance. And the independent variable is time, because the distance the car has traveled depends on how much time has elapsed in the road trip. Okay, so our variables are distance and time. And the reason that we have these in the places they are, independent and dependent, is because the distance depends on how much time has gone by. Okay, so if we're in our car and we're driving along and 1 minute has gone by, well, our distance is not going to be very much. If we've driven our car for 60 minutes, then the distance is going to change by quite a bit. So the distance depends on how much time has gone by. That's why the distance is dependent and time is independent. And a little trick of the trade is that time is almost always independent. Time is, I'm going to say that again. There are a few examples that it could not be this way, but almost always time is independent. So we've got a statement that says the way the price of a new smartphone affects number of people who buy it. The way the price of a new smartphone affects the number of people who buy it. Okay, well, we have some variables here. So one thing we have is one of our variables would need to be the price of the smartphone. So the price of the phone would be a variable. And also the number of people who buy it would be another variable. Okay. The dependent variable is the number of people. So number of people who buy it. Who buy the smartphone, right? Okay, and what would change the amount of people who are going to buy it? Well, obviously we know that it is the price of the phone that is going to affect whether we're able to buy this phone or not. So the price of the phone affects whether we're going to be able to buy the phone or not. So the number of people who buy it depends on the price of the phone. We expect the number of people making the purchase to decrease as the price increases. So we expect that as the price increases, that the number of people who buy it would decrease. Okay, as the price of the phone gets higher, because this affects, the price is going to affect the number of people who buy it. The price gets higher, the number of people who buy it gets lower. And just the opposite would be true. As the price got lower, maybe the number of people who buy it would get larger or bigger. Okay, the effect of income tax on government revenue. Okay, so we would have a variable that is income tax and another variable that would be government revenue. The dependent variable is government revenue. So government revenue is basically how much the government makes. Well, where does the government make money? They make money from income tax and other taxes as well. But in this example, we're talking about income tax. So as the government revenue, we would expect that the government, or the amount of money of the government makes, is going to go up as income taxes go up. Obviously, the more money we're going to pay in, the more the government's going to have. Okay, in the last example, it says the way in which the population of endangered elephants depends on the number of park rangers enforcing anti-poaching laws. So instead of writing these out, we've got one of our variables would be population of endangered elephants. That's going to be variable number 1. And the number of park rangers enforcing anti-poaching laws would be variable number 2. Well, you would expect if we had a whole bunch of park rangers that are enforcing the laws, so our park rangers, it's going to affect the population of endangered elephants. Okay, that should have a relationship. As the park rangers go up, the population of elephants should do the same thing. If you don't have any park rangers enforcing anything, then the population of elephants would go down. So if they either both go up or they both go down. The number of park rangers are going to affect that population of elephants. An ordered pair is always listed with the independent variable first and the dependent variable second. When you're listing a coordinate pair, we list X and then Y. X is always independent, Y is always dependent. And they've got another example here. If you're doing time and temperature, what did we say? Time is almost always independent, so they've got time first and temperature second. So Y equals f of x, read Y is the function of x. Y is related to x by the function f. So this is like just an example. If you put this independent variable in this box and we perform some function on it, kind of like magic, right? You put the variable in the box, you perform some function on it, and it spits it out as something new. Whatever we're putting in there is going to be impacted by something, and then it's going to be spit out a different thing. So a function describes how a dependent variable changes with respect to one or more independent variables. When there are only two variables, they are often summarized as an ordered pair with the independent first. So we've got the independent variable, which is your x, and the dependent variable, which is your y. The dependent variable is a function of the independent variable. If x is the independent variable and y is the dependent variable, you would write the function as y equals f of x. Okay. So example 2, for each situation, express the given function in words, write the two variables as an ordered pair, and write the function with the notation y equals f of x. So our first example says, you are riding in a hot air balloon. As the balloon rises, the surrounding atmospheric pressure decreases, causing your ears to pop. Okay, so the pressure depends on your altitude. The pressure depends on your altitude. So we say that the pressure changes with respect to altitude. So the pressure changes with respect to altitude. Okay, pressure is dependent. It's the dependent variable, and altitude is the independent variable. So it says, for each of these situations, express the given function in words. Write two variables as an ordered pair and write the function. So if we're going to write our two variables as an ordered pair, you always write the independent variable first, and pressure is dependent on the altitude. So we wrote independent variable first and dependent variable second. So the ordered pair of the variables would be altitude, pressure. If we let A stand for altitude, and that's what usually you would do. You would usually use the letters that are there to represent what you're trying to represent. And P is pressure. Then our function that we would write is the pressure is equal to F of A. So the pressure is a function of altitude. Okay, the pressure depends upon the altitude. We're plugging the independent variable into something and we're changing the pressure. You're on a barge headed south down the Mississippi River. You notice that the width of the river changes as you travel southward with the current. Okay, so the river width depends on your distance from the river source. So depends okay. So we say that the river width changes with respect to the distance from the source. So the river width is dependent variable and the distance from the source is going to be independent. So we always put the independent first. So the distance from the source, comma, river width. Okay, this is my independent variable. This is my dependent variable. So if we let W, let's let W represent the width, the river width, and we let D represent the distance, then our equation would be, well, the river width is a function of the distance from the river source. Okay. There are three basic ways to represent a function. You can use a data table. We can represent a function with a data table, which provides detailed information that can become unwieldy land. That is not what that's supposed to say. Hold on one second. We can represent function with a data table. A table provides detailed information, but can become unwieldy when we have large quantities of data. We can draw a picture or a graph of a function. A graph is easy to represent, to interpret, and consolidates a great deal of information. We can, number 3, write a compact mathematical representation of a function in the form of an equation or formula. In the remainder of this unit, we'll explore the use of graphs to represent these functions. Okay, so let's look at some of this stuff. Talk about domain and range. Domain always represents X, range always represents Y. Before drawing any function, you must determine the variables that should be on each axis. So we've got a table here, which is one way that we said we could write our graph. Another place in here we said always, if you're doing time and temperature, time is going to be your X, temperature is going to be your Y. Time is always independent. I'm going to take that back, almost always. Temperature is mostly going to be dependent. Okay, and so you can look on the x-axis, they've got their time. The y-axis, they've got their temperature here. Okay, and they've used this to graph. So the domain is down here with X and the range is up here with the Y. Okay, so if we kept looking at this and we plotted these temperatures, what are they going to look like? So at 6 a.m., I have about 50 degrees. So I would have a point somewhere around right here. At 7 a.m., so I'm going to move over just a little bit. I know they don't all have this labeled, but we're going up a little bit to 52. At 8, I would go up a little bit more to 55. Okay, and these would all be coordinates that I'm plotting. Okay, and we could finish plotting all these points and see if there's any kind of relationship on our graph. And that's what they've got down here. The domain of a function is a set of values of the independent variable that both make sense and are an interest of interest for the function. The set of values of a function that both make sense and are of interest for the independent variable. That's going to be the domain. Domain's going to be talking about our x. Domain is also independent. Sorry, independent variable. Range is going to be talking about y, and it is our dependent variable. So the range of a function consists of the values of the dependent variable that correspond to the values of the domain. The values of the dependent variable that correspond to the values of its domain is what you need to look at when you're looking at the range. So they've gone down here just like I was starting to do up here, and they're plotting these points. So the first one is 6:50, 7:52 would be the second one, 8 o'clock, 55. And so this is what they've got, all the points plotted down here. And they've labeled this time after 6 a.m. And we kind of talked about this, that as it's cooler in the morning, goes up, it reaches a peak, and then it starts to come back down as the sun starts setting. Okay, same thing on this. They've kind of stretched this out because these other quadrants, we don't have negative temperatures, so we're not really interested in those quadrants. So it would really be important that we stretch out this first quadrant and look at what's happening. So this says temperature during one day. And you'll notice they've kind of drawn two lines saying, okay, we're going to skip some data. We're going to say straight from 0 to 50. But you have to say, and that's why they've got those two little lines there saying they're going to do that. Okay. A model's predictions can only be as good as the data and the assumptions from which the model is built. So when you're creating a graph, and using graphs of functions, it's going to be important that you can identify the independent and the dependent variables of the function. You're going to need to be able to identify the domain. Those are the values of the independent variable, and you're going to need to be able to figure out what is the range, which is going to be the values of the dependent variable of the function. Use this information to choose the scale and labels on the axis. Zoom in on the region of interest to make the graph easier to read. Step number 3, make a graph using the given data. If appropriate, fill in the gaps between the data points. Before accepting any predictions of the model, be sure to evaluate the data and assumptions from which the model was built. Okay, so how do we go about doing this? We've got an example down here. It says, imagine measuring the atmospheric pressure as you rise upward in a hot air balloon. The table shows typical values you might find pressure at different altitudes, with the pressure given in units of inches of mercury. This pressure unit is filled with the barometers that measure pressure by the height of the column of mercury in the tube. Use the data graph and function showing how atmospheric pressure depends on altitude. Use a graph to predict your atmospheric pressure at the altitude of 15,000 feet and discuss the validity of your prediction. Okay? So this is one of my favorite parts of mathematics. It's being able to make predictions about things. because it's so valuable to us as humans to be able to do that. So we have to have, so of course we have some kind of thing, a table that they've given us up front. This is our information they've given us up front. Altitude in feet, and we've got pressure inches of mercury. This is on our table, this is our X, so we know that this is independent. And this is our Y, so this is dependent. So it looks like the pressure depends upon the altitude. Okay, some other things I'm noticing is this goes from 0 to 30,000. So when I'm wanting to make my graph, I'm not going to want to go up by ones because I would never be able to get that finished. So 0 to 30,000, I'm going to want to skip some. And in fact, they've gone up by 10,000s here. So they've labeled every other one. And they've got their scale drawn. Now you'll notice that the distance is the same. This is 0 to 10,000. Your first little unit is from 0 to 10,000. Then they added 10,000 more to get to the next one and 10,000 more to get to the next one. And that included all of them. But they have to be the same distance apart, but you don't have to go up by ones. Okay, on this, we've got it from 10 to 30 on here. And it looks like they've chosen to go up by fives, which is perfectly fine. It wouldn't have been as crazy to go up by ones here just because we have, I mean, it just goes to 30. But 5 is also reasonable, okay? So the first point that we want to plot is 0, 30. So we would go to our graph, and it looks like 0, 30 might already be plotted for us. It's right there. The next one is 5,025. So I'm going to go halfway in between 0 and 10,000 to get 5,000. And then I'm going to go up to 25, and I'm going to put a dot. Okay, the next one is 10,022. So 10,000, a little bit higher than 20 to get 22. I'm going to have to approximate a little bit. Okay, 20,016. So 20,000, a little bit more than 15. So I'm looking kind of eyeballing this over here. Here's 15, and we want a little bit higher than 15. And then 30,000 is 10. Okay. So if I want to use this to model and make this prediction, it says use the data to graph the function showing how atmospheric pressure depends on altitude. We did that. Use a graph to predict the atmospheric pressure at 15,000 feet. So they're wanting us to kind of go 15,000 feet right here. So what would be my pressure? Now, we could use our graph. I'm going to do this real quick. And we could try to draw maybe, I'm going to use a different color. I'm going to start up here. Now, when you're doing this, you want to try to pick, this is called a line of best fit, okay? But you want to try to hit as many points as possible. And I'll tell you why I picked here. This is not perfect, but I've got a couple of points that are underneath this line and a couple of points that are over this line. So I can use this to estimate what 15,000 would be. If I go up to 15,000 and then I go over, okay, that's going to give me a value. It looks like it's between 15 and 20. Okay, it looks like it might be a little bit closer to 20. Now, I know I didn't draw my line perfectly straight. I'm going to say probably around 18. Okay, and 18 atmospheric pressure in inches of mercury. So I'm going to make this prediction at 18 inches of mercury. And I'm saying that 15,000 feet in altitude is going to give me about this value. I'm using this to make this prediction. Okay. So using the graph, we predict that the atmospheric pressure at 15,000 feet is about 18 inches of mercury. Because we've sketched the function only roughly, we should expect this prediction to be approximately, but not exactly correct. So yes, we think it's really close to 18, but it may not be exactly 18 because we've kind of had to sketch this out. It didn't make a perfect line, but we can use this to make some kind of prediction. Okay. It's just not, I guess, it's correct down to the exact decimal place. Okay, so let's look at the next one. Okay, so this is the last example we're going to talk about, and it says the number of hours of daylight varies with the seasons. Use the following data for 40 degrees north latitude to model the change in the number of daylight hours with time. So it says the number of hours of daylight is greatest on the summer solstice around June 21st, when there are 14 hours of daylight. The number of hours of daylight is the smallest on the winter solstice around December 21st, when there are 10 hours of daylight. On the spring and fall equinoxes around March 21st and September 21st, respectively, there are 12 hours of daylight. So it says that we're supposed to kind of look at what's going to happen here. So according to this information that we've got to use this, the number of hours of daylight is greatest on the summer solstice around June 21st, and it says it's 14 hours of daylight that day. So the summer solstice has got 14 hours. I'm just jotting this down. So I went to the summer solstice, went up to 14, put a dot there. The number of hours of daylight is smallest on the winter solstice. So December 21st has 10 hours. So the winter solstice is down here at about 10. Go over, you can see 10. On the spring and fall equinoxes, March 21st and September 21st, there are 12 hours of daylight. So 12 and 12. Okay. And so what our graph kind of does is it's going to go up, come back down, then it would start to go up again because we would be going into the next year. Okay, so it says, according to the model, at which times of the year does the number of daylight hours change most gradually, most quickly, and discuss the validity of the model? So let's answer those questions real quick. We expect our number of 8 hours of daylight to be a function of the time of the year. Time is the independent variable because time marches on regardless of other events. We denote it by T. Hours of daylight is the dependent variable because it depends on the time of year, and we would denote it by an H. Okay, this time, the times of interest are all the days in the year. The domain is all the times of interest, which is the entire day. The range expands from 10 hours to 14 hours, which we can see that, of daylight. We know from experience that the number of hours of daylight changes smoothly with the seasons. So we can connect the 4 given data points for each year with a smooth curve because the same pattern repeats from one year to the next. We can extend the graph for additional years. We choose 3 years because that is long enough for the pattern to be clear. So in the book, we've just got 1 year drawn, but we could go back up, kind of continue this pattern again, and it would just keep going for another 3 years. This type of function in which a particular pattern repeats over and over is called a periodic function because the function is based on simple seasonal patterns. We can expect it to be quite accurate. Note that the curve tops out at each summer solstice and bottoms out at each winter solstice because the curve is relatively flat around those two solstices. Okay, the number of hours of daylight varies most gradually near the solstice. So that's going to answer one of our questions. According to the model, at what times of year does the number of daylight hours change most gradually? And it says that because the curve is relatively flat around the two solstices, the number of hours of daylight varies most gradually near the solstices. So at the summer and winter solstice is whenever it is going to vary most gradually. Okay. That is, we have a couple of months with long daylight hours around the summer solstice and a couple of months with short daylight hours around the winter solstice. In contrast, so that's not normal, right? Those particular times of year we have that it's 10 hours for sunshine and 14 hours of sunshine. Those months don't last very long. That's not a normal. In contrast, the number of hours of daylight increases rapidly. So that's our other, when is it most quickly? So around the time of each spring equinox, right, increases rapidly around the time of the spring equinox and decreases rapidly around the time of the fall equinox. It's going to increase here and it's going to decrease here. In other words, the length of the day changes most quickly near the equinoxes. You can observe these facts easily if you observe changing number of daylight hours over the course of the year. A perfect example of this is I really started walking, I guess, in August. And back in August, it was stayed daylight till like 8 o'clock at night. This is before the time change, but within a month, I would find, because I tried to go really close to dark because I wanted to be cooler, and I couldn't handle a whole lot of heat. So I would try to go almost about an hour before it got dark, so it would be a little bit cooler outside. Well, after about a month's time, it wasn't getting dark at 8 anymore. It was getting dark at 7. Okay, because these hours start decreasing and getting closer and closer together the closer we get to these solstices. Okay, so those are when they're during these equinoxes are when they're increasing and decreasing the most rapidly. So we have 2 more sections to do. No, I'm telling you that's not true. We have 1 more section to do, which is chapter 9B. And on Wednesday's class, I will record 9B, and I will also record 9B support. So we're getting very close to wrapping this stuff up. This was section 9A. And that's the end of this section.